Okay, this is a screencast to walk you through Unit 6, Bellwork number 3. And a lot of these can be found in your textbook pages or on some of the previous Bellwork that we've done, etc. You guys have already learned that the speed of light is 300,000 kilometers per second, but that's a speed. I want to know how many kilometers a beam of light could travel if it traveled for one entire year. So 1 light year is the distance that light can travel in a year, and it's equivalent to a whole bunch of kilometers. Okay? It's actually equivalent to 9,460,000,000,000 kilometers. Okay? And that's not the easiest thing for us to think about or write, but if we did write it, it would look like that. Okay? The little squiggly line just means I rounded it off. It means kind of approximately. Okay? It's 9,460,000,000,000 kilometers, or we could just say it's about 9.5 times 10 to the 12th kilometers. All right? As I do this walkthrough, I'm going to periodically tell you to do a doodle here or there just to prove that you're listening. And I will look for those when you show this to me. All right, so 1 light year is the distance that light travels in a year, and it's about 9.5 trillion kilometers. The next thing that I ask you about is I have several things in a chart, and I'm asking you some questions about which objects are furthest and things like that. Well, the problem right now is that all 4 of these objects, I gave you distances, but the distances are in different units. Okay, so M51, which is also known as the Whirlpool Galaxy, is 23.16 MLY. Well, what on earth does that stand for? MLY stands for millions of light years. Okay? KLY stands for thousands of light years. K meaning kilo. Kilo is 1,000. If you ever see that. And as you guys do your My Favorite Universe project, you might see some of those abbreviations. All right, then Saturn is given as 8.54 AU. Remember from page 280 and 281 that AU stands for astronomical units, which is a common unit that we use when we're talking about distances within our own solar system. Because 1 astronomical unit is the distance that the Earth is from the Sun. And so it's basically like, this is basically saying Saturn is 8.5 times further from the Sun than we are. Okay, so that's a convenient way of thinking of it. All right, then the Moon's distance is given in kilometers, 384,000 kilometers. And then finally we have the Andromeda Galaxy, which is also given in kilometers, even though it's in scientific notation. So this is kind of a nightmare at first, but we can do this. It's just we're going to do some converting, okay? All right, so before I change out my little paper, here's what I want you to do just to prove that you're listening. Where you see the KLY, where it says thousands of light years, would you please put a box around that? You're not going to see me do it, but I expect you to do it just to prove that you're following along. Okay, so my first hint to you guys was let's get everything converted into the same unit. And I picked kilometers. You can convert any of these into any unit, but kilometers kind of makes sense because kilometers is something that we're all kind of familiar with. So Galaxy M51. I have to take the 23,160,000 light years, okay? I just put it over 1 to make it look like a fraction, because then I have to multiply it by how many kilometers is equivalent to 1 light year, okay? So I have to multiply the 23 million times the 9.5 times 10 to the 12th. Light years cancel out because they're catty corner. And my answer for M51 Galaxy winds up in kilometers. It's a whole bunch of zeros, so it's just 2.2 times 10 to the 20th kilometers. Do I expect you to write down this conversion? Yes, I do. Okay. because I've done it for you. The least you could do is, follow along and write it in. Okay, the second one that we need to convert into kilometers is Saturn. Saturn's distance is given in astronomical units. And so we take 8.54 astronomical units. We're going to put it over 1 just to make it look like a fraction. And then we're going to multiply it by a conversion factor. There are 150 million kilometers in every 1 astronomical unit. Notice that AU, astronomical units, are catty corners, so those are the units that we're going to cancel out. And we're going to wind up with a number that's in kilometers. So when we do that, Saturn's distance is 1,281,000,000 kilometers. Okay? So I have M51 in kilometers, I have Saturn in kilometers, I have the Moon in kilometers, and I have the Andromeda Galaxy all in kilometers. And now, since they're all in the same unit, it's a little bit easier to compare them. Okay? So which object is going to be furthest away? Order the objects from closest to furthest. Well, let's kind of answer these two at the same time, because once we do the math, we can answer both questions. Okay. So the Moon, and I even went one step further, and I went ahead and put all of the answers in scientific notation. The Moon is 3.84 times 10 to the 5th kilometers, so that's going to be the closest. And that should make sense. The Moon is closer to us than anything else in space. Saturn is going to be 1.281 times 10 to the 9th kilometers. Andromeda Galaxy is 2.41 times 10 to the 19th. That came straight from the table because we didn't have to do any conversion on that one. And then remember, Galaxy M51, the galaxy that's also known as the Whirlpool Galaxy. We had to convert that, and when we did, we got a whopping 2.2 times 10 to the 20th kilometers. It's a long way away, okay? So, once again, I'm not going to tell you, or you're not going to see me do it, but I am going to tell you that I would like you to put all 4 of these with the numbers in scientific notation so that I know that you are, in fact, following along. Okay? Going back to the first question, which object in the table is furthest away? It's Galaxy M51. Okay? And we know that from down here. All right, the next question says a star's mass, or that's the blank, a star's mass determines how hot it is, how long it exists, and how it will end its life. We haven't really talked about this if we haven't quite finished with lesson 3, but a star's mass is the most important factor that determines what's going to happen to a star. It determines how bright it shines, it determines how hot it is, it determines how long the star lives. Mass determines kind of how the star is going to end its life, because really big stars kind of blow themselves up in a supernova. Smaller stars like our sun end their life a little bit differently as like a planetary nebula. So mass determines pretty much everything about a star. Okay? All right. The next question, again, hopefully you are listening and following along. The next question says to name and describe the different types of galaxies. And just to prove that you're listening again, I would like you to draw a little smiley face right beside the number 4. Okay? And you're not going to see me do it, but I want you to do it. Okay? So a little smiley face right there. All right. These 3 types come straight from lesson 1. Galaxies that are considered to be irregular don't have any real shape, particular shape to them, so they're just kind of, look random. Elliptical galaxies look either kind of round or oval. Spiral galaxies have arms that kind of spiral or curve around, and they kind of look like a pinwheel, or they kind of look like a hurricane. If you've ever seen the way a hurricane from a satellite image kind of looks. Okay. By the way, our home galaxy is the Milky Way galaxy, and our home galaxy is a spiral galaxy. Our solar system is out in one of the spiral arms. Okay. There are actually a couple of other galaxy types, but we're not going to get into those in detail. But you might want to, well, not that you might want to write them down. I do want you to write them down. There are other types of galaxies. There are some galaxies known as barred spiral galaxies, which kind of look spiral, but they kind of look like they have a bar sort of running through their center. And then there are galaxies that are called lenticular galaxies, kind of lens shape. Okay. All right. So there's been a couple of listening hints along the way. Make sure that you've done those. Okay, so now I'm on the back of Unit 6, Bellwork number 3. And we've just done some activities. We did the star sort activity and we did the who's who. And those were both things that at least part of the activity dealt with magnitude or brightness. So number 5 says a star's brightness as seen from Earth is its, and that's going to be its apparent magnitude. Like how bright the star seems to be from Earth is its apparent magnitude. And apparent magnitude is going to depend on two things. And you guys have told me this repeatedly in class. You know that how bright a star seems to be is going to be influenced by how far away it is. The sun appears really, really bright to us just simply because the sun is so close to us. It's not really that the sun is a very bright star. There's a whole lot of stars out there that are a whole lot brighter than the sun. So a star's brightness depends on distance. And the other thing it depends on is its luminosity, or how much light it's actually giving off. Okay? And how much light it's actually giving off, that's called absolute magnitude. So it kind of depends on absolute magnitude plus distance. Okay? And then that leads us to number 6. The actual brightness of a star is luminosity, or absolute magnitude. It's a measure of how much light a star is actually emitting. Okay? And you're going to see luminosity and absolute magnitude. Those things, those two terms can be sort of used interchangeably. They mean basically the same thing. Again, we've been doing this the last couple of days. On the magnitude scale for star brightness, stars with lower numbers, or stars that are deeper into the negative territory, are brighter than stars with larger numbers. Okay? So the lower the number, the smaller the number, the brighter the star. Okay? So lower numbers are brighter than stars with larger numbers. And then finally, we go to page 288, if you don't already have this kind of memorized. The color of the coolest stars, remember our spectral classes go O, B, A, F, G, K, M. M are your coolest stars, and those happen to be the color red. Our sun is a yellow star. It's about medium, medium temperature. And then the hottest stars are actually blue. All right, just to prove that you listened the whole time and didn't just tune me out, I would like you to draw your best little minion down here. Okay? So put your little minion down here, and then you are going to turn this in. Okay? Thanks so much.